As computing systems gained popularity, so did the world of multitasking, so that processing systems became further refined and created this illusion of multitasking better.
On this episode of Embedded Insiders, we're discussing the evolution of processor cores, multitasking capabilities, and the future trends involving processor design and more with Aaron Frank, Senior Product Manager at Curtiss-Wright Defense Solutions. Then, to continue our Engineering Heroes series sponsored by Wind River, we're highlighting Anton Ristrom, Defense Manager at Acker Solutions, an engineering company that focuses on building infrastructure for renewable energy solutions. But first, in case you missed it, Rich and Ken are giving some insight into their trip to Nuremberg where they attended Embedded World 2024.
Hey folks, welcome to the Embedded Insiders podcast. I am Ken Briota with Embedded Computing Design, and I am so happy to be here with Rich Nass, also of Embedded Computing Design. Welcome, Rich.
Thank you very much. How you doing?
Oh, I'm doing all right. You just about recovered from Embedded World? What did we get back 4 days ago?
Well, this is where you say, I just flew in from Nuremberg, and boy, are my arms tired.
This is no one should ever say that, Rich. I'm sorry. We're not in the Borscht Belt anymore.
Yes. You're right. Okay, so I am recovered. Let's see. It was a great show, actually, from most of the different benchmarks. The number of people, they had a number of 32,000 visitors. I don't know if I believe that, but it was packed. There was a lot of people there. There was a lot of buzz.
That exhibit hall was never easy to walk through, and that's a good sign of how busy everything is. You know, it was always trying to go. You had to leave extra time to get from one place to another, and I know it's a little amorphous, but the vibe was good. Like everybody seemed excited, seemed really positive. There wasn't a lot of that. You know how sometimes you're at a trade show and there's that talk about like, well, I don't know how it's going to look in 6 months, or, oh man, everything, we're really having a hard time right now and we're focused on whatever, I didn't hear any of that kind of talk.
Well, people are still riding the AI wave, and I think we're going to see that for some time now.
Sure.
We're just sort of having iterations and people are trying to figure out what's going on. It was interesting. I saw a release the other day that Microchip just acquired an AI company. So that's their way in. Interesting little side discussion. There's two different paths people are taking. Some of them are doing it. Some of them are getting into AI organically, but the majority of the folks are doing it through acquisition.
That's kind of become like de rigueur for tech companies now. It's, the startups are developing the tech, and then the bigger companies are waiting and buying the startup. And so many of these startups are built with that goal in mind now. I don't know if I want to make a judgment call about how healthy that is for the market, but it seems to be the way things have been working the last, 8 or 10 years.
Yeah, for sure. You could sort of figure out, who did what, but the Renesas's and Infineons and now Microchip are doing it through acquisition. Then you have Synaptics and NVIDIA, obviously, who did it through just organically building it up from internal resources. And I could certainly make a really good argument why each way is better than the other, but the proof will be in the pudding probably a year from now.
Oh yeah. And look, I don't think there's much chance of the AI wave breaking in the short term. I think everybody's going to be talking about it. Although I think there's a good chance that it moves into its proper place, in my opinion, eventually, where it's like another, application layer. It's another important element, but it's not really an industry in and of itself. It's a horizontal thing, sort of like IoT has become. People have started to understand that it's more of a horizontal thing than an industry of its own.
Yeah, I agree with that 100%. And it'll find its different applications in different places. where we sit in the industrial space, it's huge for
Yeah.
automation and smart buildings, smart cities, even smart homes.
Supply chain,
Yep.
I think that in like material science and mining and that kind of thing, it's also becoming pretty important. They're using it for surveying, they're using it for all that sort of stuff. So it's interesting. And I don't know if we're playing with trends and stuff that we heard at Embedded World. I don't know if I heard this, but in my observation, it certainly looked like the AI tools were starting to find that level. It wasn't here's our AI, it's here's our solution that includes AI capabilities, was
Yep.
more what I was
Yep.
hearing. I don't know if you felt the same.
Yeah, pretty much. And one of the demos I saw that I was really impressed with, that I have a board here that I'm ready to play with, was from Renaissance. And they were literally dragging and dropping things and having the software compile on the fly.
Wow.
That's pretty cool. So if it's real, if I can do it, I guess it's real. So we'll see. But I'm anxious to give that a try to see if I can actually emulate what they were doing on the show floor in their CAN demo.
Yeah. You know what I was surprised I saw very little of? There were a few playing with generative AI, because the way that when I was at GTC a couple of weeks ago, the way that they were talking there was that, oh, everything is generative AI, and of course that's a hype thing, but I expected more of the embedded world companies to be sort of trying to trade on that, if not actually doing a thing with it. And very few were talking about generative. I, I'm starting to think that my instinct that people aren't sure what to do with it in the industrial space yet is probably true.
Well, remember what your source is. When you're at NVIDIA, you're
Yeah,
talking an order of magnitude of compute power difference, where you have the ability to do that stuff. And more in an embedded world, when it's mostly industrial, it's good enough is good enough.
yeah, yeah. That's fair. There were a couple of companies, and folks out there listening, keep an eye on the website because there's articles coming. There were a couple of companies talking about building with generative AI capability in mind, but I didn't. I don't think I talked to anybody who had a direct application that they were
Yep.
already using. So we'll see.
Yep. And then shifting gears, no pun intended. Interesting that NXP announced a CPU that the goal of this is to consolidate all the ECUs in the automobile. It seems like we keep having a
Yeah,
discussion. Is it better to have one consolidated ECU or have them all mixed out throughout the car? And again, I can make an argument why either one is better than the other, but
yeah.
NXP was making a pretty big push on this and just having that one ECU and having everything run from that. It's a pretty powerful processor.
Yeah, and it's I've been hearing that since CES, is this debate back and forth, and it seems like the one ECU and then connecting everything via Ethernet is the solution that the OEMs are leaning toward, which I find a little bit surprising. I would think that they're trying to move away from cabling and into wireless solutions, but I guess in automotive it's a little bit more difficult to sell that idea.
Well, you actually are reducing the cabling by having the central CPU because
Oh,
you're
sure.
only going out to the endpoint or the end mechanical point as opposed to going out to the processor and coming back and forth. So you are reducing the cabling, but I'm more of the mind to have a simple CPU at each point. So when there is a failure, it's easy to fix, replace your point of
Right.
failure.
I think that the answer is probably going to be redundancy. They'll have a smaller CPU at each point, and then a main, ECU that's doing everything else, and or handling the major processing and stuff like that. But the brake systems will each have their own little
Yeah.
processor and everything else. I think that's probably the real answer. I'm sure you've seen and I've seen that the answer is always both or in the middle, or
Yeah.
it's never whichever extreme somebody wants to sell at first.
Yeah, I find that interesting as well. We have to also put in a plug for all the winners of the Best in Show, which were announced at
Oh
our
yeah.
cocktail party the night before the show opened. So congratulations to all those folks. If you go to Embedded Computing Design, you'll see all the winners.
And looking forward, we've got the Embedded World North America coming up, where we're going to be talking about Best in Show awards for that. But right now, the call for papers is open, isn't that right? Until June.
It is, and again, if you go on to embedded computing design, actually, if the story you filed, Ken, has the link to the call for abstracts. So submit your abstracts. Now's the time. And the buzz for North America while we were in Germany was
huge,
really high, and
Yeah.
people are pretty excited about bringing this show into the United States. I happen to be on the program committee, so I'm
Yeah.
excited to see all those abstracts.
Everybody knows the opportunities here. I think it's going to be really cool. And a lot of that depends on you listeners out there sending in your abstract, send in your papers, send in your ideas, because
Yep.
the more robust this program is and the more peer to peer it is, the better. So yeah, that'll be that's I think going to be really exciting.
Now, here's Aaron Frank, Senior Product Manager at Curtiss-Wright Defense Solutions, discussing the development of multi-core processors, multi-threading technologies, hybrid processors, and much more.
So historically, how have processor cores evolved over the years, and what are some of the key milestones that mark the development of multi-core processors?
I think computing processing or computer processing goes back quite a long time, back from the days of Charles Babbage and his analytical computer back in the 1800s. But if you think of the early days of modern digital computers, all processors, and if you think of everything from the ENIAC, with vacuum tubes, to the early mainframes, these were all what we called single tasking processors. That means that they could only do one thing at a time. They can follow one thread of programming. In the, I guess, mid 1960s, multitasking operating systems came into existence, and they created the illusion of multitasking effectively by running one program for a period of time and then switching to another program. And they did this context switching fairly fast. So it created an illusion of doing several things at once. As computing systems gained popularity, so did the world of multitasking, so that processing systems became further refined and created this illusion of multitasking better. But it was still an illusion. These were still processors that became faster and more capable of switching tasks from task to task quickly, but they still only executed one task at a time. And now they were context switching many hundreds of times per second, but again, still single tasking.
So can you give our listeners maybe a brief overview of this transition from single core to multi-core processors?
It was actually IBM who pioneered the first, what they called dual core processor, around the year 2000. Inside their Power 4 processor, they created an architecture where there were two processing cores that could operate at the same time. They would share memory and peripherals, but it was an absolutely brilliant way to pretty much double the processing performance. And I say brilliant because others were trying to increase their processors' performance by increasing their clock speeds as a way to increase performance. But these came at incremental steps. It was clear to IBM that computing systems were required to do multitasking better, but they were still limited to doing a single thing at a time, even with faster clocks. So this idea of multiple cores or dual core was a brilliant way to now do things twice as fast. Shortly after that, AMD followed with their dual core processor, but I think it was really Intel who truly popularized the concept with their Core 2 Duo processor, which came out around 2006. If we fast forward this to today, the concept of a dual core has grown into the multi-core processor. And today it's not uncommon to find processors with dozens of cores. And in fact, some server class processors have many hundreds of processing cores. If we take this to the extreme, today's GPU or graphics processors which are designed specifically for highly parallel processing. GPUs can have thousands of processing cores, all of which operate simultaneously, and this drives incredible parallel processing performance.
So, can you maybe explain multi-threading technology and how it's contributed to this improvement of processor performance?
Absolutely. Rather than focus on processor performance, I'm going to slightly redirect to consider the performance of a processing system as a whole. Today, we all live in a world of multitasking, and I'm not just talking about people who switch between email and social media and conversation at your dinner table. Whether it's your laptop or desktop computer, all of these computing systems are running real-time multitasking operating systems. When I looked into my simple Windows PC, which is nothing more complicated, it's just a corporate laptop, which was running 3 or 4 applications at the time. It was running an email application, a messaging application, and I think Microsoft Word open as a word processor. That simple setup was running 229 separate processors and well over 3,000 threads. Today's processing systems are doing a whole lot of stuff in the background. Now, mine was a corporate laptop, but the phone that's in your pocket is similarly running hundreds of processes and tasks while it reaches out into the world to update your email, to monitor your social media feeds, check an application updates, look for new Wi-Fi hotspots. It's also counting your steps as you walk, and it's listening on its microphone for you to call its name and give it a command. So back to your original question on how multi-threading technology contributes to performance, I think anything we can do to improve the computer system's ability to multitask will have very direct benefits to a system's performance, its responsiveness, and its capabilities.
So, can you expand on some of the different types of multi-threading technologies and how they impact processor efficiency, reliability, and any other performance factors that matter to developers? I know you touched on this a little bit.
Absolutely. Most modern processors, as I mentioned, are what we call multi-core processors, which means they can process different tasks in parallel. A quad-core processor can run 4 things in parallel, and there are, I mentioned, server-class processors that have dozens or hundreds of cores. So in most of these processors, a core is a core is a core, and all of the cores in a multi-core processor are the same. So what's new, and I think very interesting, is that there's a new term called hybrid processors. A hybrid processor is a different kind of animal. A hybrid processor is a multi-core processor, but not all of its cores are created the same.
Which leads into my next question perfectly. How do hybrid processors handle both single-threaded and multi-threaded tasks efficiently? And why is this important?
Well, as I mentioned, a hybrid processor, not all cores are created the same.
Mhm.
Some of the cores are optimized for the highest possible performance. And these cores typically consume the most power and generate the most heat. There are other cores that are optimized for the highest possible efficiency. And these cores have reduced performance, but they offer significant benefits by reducing power consumption and corresponding heat. It's a fascinating architecture, and it was pioneered by, I believe, ARM Holdings back in 2011 with what they called the big dot little architecture, where big was the name they gave to these high performance cores, and little is the name that they gave to these lower performance and higher efficiency cores. So a hybrid processor of the ARM big dot little architecture has a mix of big cores and little cores.
So why is the hybrid processor architecture important?
I'll bet every one of your listeners has a cell phone. And one of the most important features of a cell phone is battery life. And today's cell phones are capable of doing just about everything that a laptop computer can do. And it's absolutely critical that all these tasks, which consume processing power and battery life, are operating as efficiently as possible. These background tasks do not have to operate in high performance real time mode because they're in the background. Their most important consideration is battery power and the fact that they're always running. On the flip side, that same phone, when you stream high definition video content or perhaps mirror that to your big screen TV so your friends can also watch, that's where the phone needs highest performance and can sacrifice some of that battery life because nobody wants a jittery or a start stop video feed. And this is exactly where these hybrid processors shine. Hybrid core processors give the software developers that flexibility to tune a system, sometimes for performance and sometimes for power savings, or perhaps a mix of both. And they can decide on what type of applications to run on the different types of cores of a hybrid processor, depending on whether you're running real time, whether you're running in the background, whether your screen is on or off, and so on. On the, I'm going to say, more technical side, a high performance core takes up more silicon space. So there's usually not too many of those on a processor core. But these reduced performance cores are significantly smaller in silicon space, which means the folks that make these processors can put more of the reduced performance cores onto the silicon. And the net result of all of this is that these newer hybrid core processors with higher core counts can actually do a lot more things at once and at the same time do it more efficiently. To get the most benefit out of these hybrid core processors, our software developers have to have the ability to decide on what type of core to run their application on. And if we go back to your iPhone example, in fact, not just the iPhone, almost every type of phone in use today, most of them are ARM hybrid core processors. I have no doubt that the software developers for these type of devices where power savings is critical, they will consider when to operate on these efficiency cores and when to operate on the higher performance cores. And while not all embedded processing systems are battery powered, I think we all share a responsibility to use power more efficiently for a whole host of reasons.
Speaking of these newer cores and higher core counts, what do you see as the future trends in processor design, especially regarding the number of cores and thread management and multitasking capabilities?
That's an excellent question. And we all know that some technologies are fads and some have staying power. I don't think the world of multitasking is going to go away. If anything, it's getting more and more complex. So I believe that hybrid processing and the increase in core count is here to stay. In the near term, I think we can all expect to see a very quick jump in the number of cores of a processor. The consumer world has had a very flat number of processors for many years, the status quo being the quad core processor. And rarely would you see anything other than a quad core as your highest core count. But today, if you look at whether it's Best Buy or go in the consumer world, we're seeing an immediate jump with 12 and 14 and 16 core processors already on the market. But it's important to remember that not all cores are created equally. Most often, about half of those cores are geared for performance and the other half geared for efficiency. So while we might see significantly higher core count processors, I would say that their reasonable power consumption is also an expectation. Can you imagine, a 64 core laptop that still had its battery lasting all day? Now, at Curtiss-Wright, where I work, we design rugged embedded processing systems for the most critical applications, primarily in the aerospace and defense world. And most of these applications are embedded systems where the user's not really, I'm going to say, using a computer. Instead, they're doing something that requires a computing system, maybe flying a plane or looking at a radar screen. So the idea of hybrid processors and more efficient processing is very important. We recently introduced the industry's first Intel hybrid core processor to the aerospace and defense industry. This is a VPX processing module that incorporates Intel's 13th generation 14 core hybrid Raptor Lake processor, along with an extremely fast 100 gigabit connectivity. And given this environment, we have to develop extremely rugged and reliable processing systems in, I'm going to say, very extreme conditions. Any power savings we can design into the system have huge downstream benefits. So as we bring these new hybrid processing technologies into the aerospace and defense world, this is also a call to action, I guess, for our software development partners to start looking at these exciting new hybrid processing technologies and incorporate ways to better take advantage of them, just like the world of consumer cell phones, where you can last all day on a single charge without skipping a processing beat. As we get more and more efficient processing systems, this has tremendous benefits to everybody.
Now, here's engineering hero Anton Ristrom of Acker Solutions providing some insight into the use of computational fluid dynamics to stimulate sustainable global energy solutions like subsea compression.
With the ever-present and growing threat of climate change, sustainability is a hot-button topic and has been for years now. But advancements in technological capabilities are allowing innovators to find more and more creative, sustainable energy solutions. One such method you may not be familiar with is subsea compression, which is a way to draw naturally occurring gas out from the seabed. Compressors are placed on the ocean floor to increase pressure, which compromises the gas to allow it to flow up into pipes with less resistance. This compression process ends up generating a lot of heat, so the gas also needs to be passed through building-sized cooling chambers, and as I'm sure you can imagine, it would be pretty difficult to develop and test such a large system at the bottom of the ocean. Luckily, we have people like Anton Ristrom, an expert in using computational fluid dynamics in simulation technologies that helped greatly in projects like the 2015 Asgard Subsea Compression Project, where he and a team at Acker Solutions used that tech to develop digital twins of 17-meter-tall cooling chambers. Anton, can you tell us a bit about yourself? Where'd you grow up? What led you down the engineering path to where you are now?
Where it all started, I grew up in a really small town in the northern parts of Sweden called Arvidsjaur. It's famous for testing cars. There's a lot of car testing that's going on in Arvidsjaur. So the Volkswagen Group are coming up there. Grew up with my mom and my dad, a little sister that's 2 years younger than me, and we had 2 dogs. I think what kind of got me into engineering, or what prepped my subconscious, or prepped me for kind of making that choice later in life, was just having this fascination for how things work. I was really interested in technology and in technical stuff. I remember I liked just taking things apart and seeing what's on the inside of this. How does this work? I didn't understand, much of it. Just pretty much took it apart to see what was in there and if I could put it back together, which was not the case for all the times. So my dad was a pilot. When I was growing up, he was a commercial pilot, but before that he was part of the Swedish Air Force. So he was flying all of these different really cool fighter jets that we all got taught about in school. And my mom, she was also during a period of time working as a flight attendant. So sometimes they would actually work together, and then they had pretty much no choice than to take me and my sister on the plane with them. I started out as wanting to become a pilot and kind of follow that path. But I am super fortunate to have a very diverse work environment, and I have lots of things to do, and no day is really the same as the other one. It's filled with just collaborating with the team and trying to solve these challenges that we're working on that day. And it's a constant, like, good pace. We're all in there and we're committed to solving these problems, which is really nice to work in that environment where people are committed to solving a problem. It's not the regular 9-to-5 grind. That's not the case at all. So I really like working in that environment with my colleagues.
So how did you get into these two areas, this intersection between simulation technology and computational fluid dynamics?
Yeah, so I started my career in 2019 as an engineer, as a simulation engineer for computational fluid dynamics, it's called, simulating fluid flow. And kind of quickly went into a role with more responsibilities. So kind of managing or directing a team on a technical level in how we can perform the best as a unit. In the northern part of Sweden, we have a lot of activity relating to space, and we have satellites, launch sites, and things like this. So space was also a big interest for me when I was small, and I found out that a city not too far away from my hometown was actually had an education, a space engineering education. So I just simply applied for that and got in, which I was really happy about. And that kind of got me into the aerospace track. So space and aerospace are quite closely related when you are studying. And with aerospace, I quite quickly got back into airplanes and engineering with respect to airplanes. And that's kind of when we started doing simulations on wing profiles and on these winglets that can optimize or reduce the fuel usage for an airplane, for example. So these kind of simulations, coupled with the really graphic, visual, strong representation that you get from CFD simulations, that's just kind of started a spark in me, and I felt like this can be something. I think this is fun. It's it has huge potential in the future, and as you say, it's something that's in constant growth and getting bigger and bigger. And the more digitalized we become, the more we should rely on simulations to sort of point us in the right direction.
Can you tell us about your role with Aker Solutions and the subsea compression projects you and your team worked on?
The company I'm working with right now is called Aker Solutions, and we have a lot of different technologies that we are working with to solve this super important task that we are all faced with, which is the energy transition. So transitioning into a more sustainable way of living and providing energy and affordable energy and reliable energy for everyone. And one way of doing that, we believe, is through a technology called subsea compression. And that means that you're building a station that has compressors and putting that right on the seabed where you have a natural gas, and increasing the pressure already at the seabed, and that compromises the gas so it flows more easily through the piping. It reduces the resistance, so to say, and essentially makes taking up natural gas more efficient than traditional methods. CFD can be put to use for so many applications when doing such a big project that this is. We are, for one example, developing coolers, enormous subsea coolers, the size of an office building, pretty much 17 meters tall, that cools this natural gas after being compressed, because the compression increases the temperature of the gas, and that needs to be cooled to prevent any damage from occurring on the downstream system. So with CFD, we can create these coolers in a digital environment and adjust design parameters to see how that affects the cooling of this gas. And by doing this, we can move away from testing, which is very time consuming and very expensive, and instead doing this in a digital domain. So that's one of the examples of the big strengths where CFD plays a huge role. So our first subsea compression project that actually went into the sea, that was done together with Statoil, or who are now Equinor. It's been described running like a Swiss watch, pretty much. I think that it's planned to be installed in 2025. So we're getting closer and closer.
That definitely sounds like a really complex undertaking. Was there anything that was particularly difficult for you and your team while you were working on these simulations?
It's something that's new, and it has so many different challenges. Everything is just beefed up. It's bigger. It's a higher flow of natural gas, for one example, and it's just so many things that are more difficult and more challenging. And but that's a part of what makes it fun to go to work, because it is challenging, and it's a challenge. And when you crack that tough nut, then it's instant.
And have you found that there are any specific skills or characteristics as an engineer that have helped you overcome challenges like that?
Yeah, I think along the way you pick up a lot of new skills and a lot of new insights, and it's really good to have an open mind and a willingness to learn. So I am curious at every corner. I have that sort of want to learn mentality, and I'm also not afraid for a challenge. It's good to be challenged.
So you've been able to implement CFD in projects like these ones for subsea compressions, but what other kinds of applications have you been able to apply that knowledge?
We apply CFD on many different projects around the company. We're involved in everything from subsea processing and subsea compression projects that I mentioned, to simulating, power cables for electrification, and looking at looking at systems for offshore wind farms. How can we optimize how much current is going through this cable that leads up to a wind turbine, for example? We're using CFD to optimize a structure that's required for offshore fish farming, for example. So when waves hit the fish farm, how big are those forces, and can we optimize the design somehow to meet different criteria? I like that CFD is being considered more when starting a new project. So that's going to be interesting to see, CFD developing and becoming more and more used. And as I said, it can be used for almost anything. So in the energy transition, I think that CFD and simulations plays a huge role.
And what's your favorite part about doing what it is that you do?
What I love about my job is that we're solving actual problems, and we can actually see our ideas coming to life in a workshop. So the things that we do our simulations about, the things that keep us up at night, that we struggle so much or fight so much to, the challenges that we are solving and working so hard to solve is being made into reality, and being used in the real world to solve one of our biggest challenges. That's what I love about my job. It's very inspiring.
Now, Anton mentioned that he led a team at Aker Solutions, and one of those team members is system engineer Jesper Persson. Jesper, can you tell us a bit about yourself and your background?
My name is Jesper Persson, and I work currently as a system engineer in Aker Solutions in our Gothenburg site in Sweden. I've been working here for pretty much 2 years, straight out of school, at a university. So my background is I've done a bachelor in mechanical engineering, and I did my master's degree in applied mechanics, focusing a lot on what you call fluid dynamics, which is a lot of what we do here in the Gothenburg office. That's not really my role now. I think that's kind of typical for engineers to study one thing, but then you end up working with something else. So as a system engineer, I keep a kind of a broader perspective, and in a lot of ways you can call it a project management role in a way, or at least assisting the project managers, kind of being a jack of all trades in a way, to know a little bit about everything, to kind of piece the experts' knowledge together into one system product.
What would you say is the most important aspect of working among a team like this one at Aker Solutions?
So I think there's in terms of collaboration, collaboration is super important, right? Because if you're an expert at a subject, you must, everyone knows something, but no one knows everything, of course. So it's very important with the collaboration between these experts. You could be a process engineer, you could be a system engineer that I am, you could be a CFD engineer that Anton is working a lot with. They all kind of, everyone pulls together in a way to add their expertise to if it's a problem or if it's a design improvement or whatever. It's really important to get everyone's take in a way. So I've never encountered that we had a specific issue or something that we wanted to do where there's only one person involved that knows everything basically. So it's always a team effort, right? But the cool thing about actually going out in the field to if we say test things, it's that you get a much deeper understanding of what you're working with. So of course it's also fun to see the things that you've been working on for a year, to actually see them in person in a way. But also to get that deeper level of knowledge, I think you have to kind of touch things and feel them and see them in action and in operation live. So I think that's been a super rewarding experience as well. And it's also like that's what it's all about, right? Because you're gonna test that it actually works. So it's it's almost like a nervous feeling, right? Because you're looking forward to it, but it's also like it's a moment of truth in a way. So you're really looking forward to seeing that the things that you've been working on that they're complete and that they're also work as intended.
Are there any specific traits you've seen in Anton that have made him particularly successful as a team leader?
I think, of course, I worked with Anton, and I think one thing that he does really well is that he brings out the best in the best ability out of people, or the best that they can be. So he is working a lot with younger engineers. He's a manager as well, so typically for younger engineers, and he was my manager when I started in Aker Solutions. So he's really good at kind of finding the quality in people and helping people achieve the things they want to achieve and grow pretty much. Because of course, when you're fresh out of school and you're a young engineer, I think if you end up in the correct place and you're kind of challenged in a positive way in your work, I think you can learn so much in such a short time span.
And what kind of characteristics would you look for in younger, aspiring engineers that would set them up for success?
I think an important thing when you are working as an engineer, or if you're an aspiring engineer and you're in school or whatever, I think it's important to be curious about things. To be curious about things when you're in school, and to be curious about things in your work life, to kind of keep expanding your own knowledge in a way, and learning things along the way. Because I think it's easy if you sometimes, of course, people get busy in their work life and in school as well, for sure. But to kind of make time to be a little bit curious and just read up on things that maybe you have a deadline on a project or whatever, and you need to get that done. But don't just focus on the things that you have to do. Focus on the things that you're interested in as well, and that goes for if that's technology. If you're planning to be an engineer and you're interested in technology, be curious about that, or whatever it is. But I think it's important to keep that mindset going through, and to be curious about the things that you're working on.
Thanks for listening to this edition of Embedded Insiders. For more daily news, videos, and podcasts, visit our website at embeddedcomputing.com.